The universe had only a few minutes to build its first elements. It built almost nothing. Your species arrived late. About 13.8 billion years too late to watch the first nuclei form. There is no camera pointed at minute 3. No photograph. No recording we can replay, frame by frame. And yet the event did not disappear. I find it in quasar light passing through distant gas, in the minute offset, between hydrogen and deuterium absorption lines, in the amount of helium inside, regions barely touched by generations of stars, and in the pattern of the cosmic microwave background written hundreds of thousands of years after the nuclear reactions had ended. Humans call these values primordial abundances. Correct, but incomplete. I read them as an execution log, the final output of a network of possibilities that ran for only a few minutes, then ran out of time. The log is remarkably short. Vast amounts of hydrogen, almost 1/4, helium by mass, traces of deuterium and helium, 3. Then a vanishing amount of lithium. That is all. The universe was hotter than the core of any star alive today. Nuclear matter was everywhere. Energy was not scarce, and gravity did not need to gather fuel. Inside a star, by human intuition, it should have been the perfect factory. It was not. Extreme heat did not accelerate construction. It prevented the first fragile piece from surviving. By the time the temperature became useful, expansion had already reduced the density and started a clock no reaction could stop. This is the question I cannot ignore. How did the universe turn a nearly missed window into a recipe we can still measure? I will not take you there with an imaginary camera. I will do something more honest. I will begin with the traces. Then I will reconstruct the network that made them. At the end of the first second, the universe contained protons, neutrons, electrons, neutrinos, and a sea of photons. It contained no atoms. A free proton was the future nucleus of hydrogen, but it would wait roughly 380,000 years before it could keep an electron. That distinction looks small, only if you ignore almost all the physics between a nucleus and an atom. The previous episode left us with two clocks, the interaction rate and the expansion rate. While reactions ran faster than space expanded, particle populations could track equilibrium. When expansion won, a temporary state became a cosmic inheritance. Now I add a third clock. A free proton is stable, as far as we can measure. A free neutron is not. Outside a nucleus, a neutron decays into a proton, an electron, and an antineutrino. Its lifetime is on the scale of 15 minutes. That is brief by human standards. For the infant universe, it was long enough for nucleosynthesis to begin, but short enough for every delay to change the final recipe. In the hotter plasma, weak interactions converted protons into neutrons and neutrons into protons. As long as those reactions kept pace with expansion, the ratio between the two populations tracked the temperature. As the universe cooled toward the scale of 1 megaelectronvolt, the weak interactions began to fall behind. The ratio did not freeze in a single instant, but it drifted out of equilibrium. Neutrons, slightly heavier and now unstable, continued to disappear. By the time nuclear reactions became efficient, roughly 1 neutron remained for every 7 protons. That was the helium budget. This ratio was not chosen after the fact to explain what astronomers found. It followed from the neutron-proton mass difference, the temperature response of the weak interaction, and the speed at which space expanded. Change the expansion rate and the weak reactions lose equilibrium at a different temperature. Change the neutron lifetime and a different number of neutrons reach the nuclear starting line. Primordial helium therefore tests more than nuclear physics. It is sensitive to gravity, the weak interaction, and the radiation content of the universe. Additional relativistic species would have accelerated expansion, preserved more neutrons, and raised the helium fraction. Measuring helium can constrain particles that may have existed then even if they are no longer visible now. Helium contains 2 protons and 2 neutrons. If nearly every surviving neutron ends inside such a nucleus, the neutron count sets the amount of helium almost directly. The reaction network is complex, but its dominant result can be understood with simple arithmetic. 1 neutron for every 7 protons means that about 2 of every 8 nuclear particles can be locked into helium-4. By mass, the result is close to 1/4 helium and 3/4 hydrogen. Not exactly. Real calculations include neutron decay, neutrino heating, nuclear reaction rates, and small thermal corrections. The estimate survives because it captures the structure of the problem. Primordial helium is a record of how many neutrons were still available. Those neutrons had to be protected inside nuclei before they decayed. The first possible shelter was deuterium, 1 proton bound to 1 neutron. The network could build it. Light destroyed it. Deuterium has a binding energy of about 2.23 megaelectronvolts. It is tempting to assume that deuterium began accumulating as soon as the average temperature fell below that value. It did not. There were roughly 1 billion photons for every particle of ordinary matter. The average photon could carry less energy than deuterium needed to break, while the high-energy tail still contained enough violent photons to destroy the fragile nuclei almost as soon as they formed. That billion-to-1 imbalance changes the intuition completely. A temperature is not a box in which every photon carries the same energy. It describes a distribution. Most photons may have become harmless to deuterium, while a tiny fraction remained energetic enough to undo the bond. When photons outnumber baryons by about 1 billion-to-1, even a tiny fraction can overwhelm every new nucleus. The average had already crossed the apparent threshold. The dangerous tail had not. A proton and neutron joined. A photon split them apart. They joined again. Another photon erased the result. The process repeated without intention and without frustration. Only probabilities running through an immense plasma. From my perspective, there is no single scene. I see the entire reaction network at once, and almost every path closes at the same node. The first bond does not survive long enough for the next reaction to use it. Physicists call this delay the deuterium bottleneck. The universe had raw material and allowed reactions, but it lacked a first step that could survive. Without stable deuterium, no significant flow could reach helium-3, tritium, and helium-4. Picture a bridge whose first span is installed again and again while a current rips it away before the next span can be attached. Protons and neutrons wait on one bank. Much more stable helium lies on the other. Between them, the first connection refuses to hold. The analogy helps you. I do not see a bridge. I see almost zero flow through a mandatory node. Nuclei do not wait in line, and photons attack nothing by intention. Every reaction has a probability, and the plasma held an enormous Distribution of energies. The average energy did not open the route. The number of photons energetic enough to destroy the first bond had to fall far enough. Only when the temperature dropped toward 0.1 megaelectronvolts did those destructive photons become scarce enough. The universe was already a few minutes old and far less dense than before. Deuterium began to survive. For the first time, a deuterium nucleus had a reasonable chance of remaining intact until the next reaction. Flow through the network surged. The window had opened. Not for long. The late start is why neutron lifetime matters so much. During every minute of the bottleneck, some free neutrons decayed. If deuterium had become stable earlier, more neutrons would have entered helium. If it had become stable later, the helium fraction would have been smaller. The temperature near 0.1 megaelectronvolts is not merely a point on a timeline. It connects the photon spectrum to the final chemical composition of the universe. Once deuterium remained intact, the network moved quickly. A deuterium nucleus could capture a proton and form helium. 3. 2 deuterium nuclei could produce tritium or helium. 3. Those nuclei followed different paths toward helium. 4. 2 protons and 2 neutrons in an exceptionally stable configuration. Helium 4 was the natural destination of the fast network. There was no single assembly line. Deuterium reacted with protons, neutrons, or other deuterium nuclei. Tritium and helium 3 offered separate routes. Forward and reverse reactions competed inside the hot plasma. What survives today is the integrated result of the entire network while temperature changed, not the product of one reaction running under fixed conditions. Laboratory experiments measure the cross-sections of these reactions. The probability that 2 nuclei at given energies will produce a specific outcome. Some measurements happen deep underground, so rare signals are not buried under cosmic radiation. At Gran Sasso, the Luna experiment measured more precisely. The reaction in which deuterium captures a proton, emits a photon, and becomes helium. 3. A correction made by an accelerator beneath a mountain improves our reading of ordinary matter density in the first minutes. The connection is unusually direct. Change the measured deuterium burning rate in a standard BBN calculation leaves a different amount of deuterium behind. Compare that prediction with absorption in ancient gas, and the surviving ratio points back to baryon density. The underground accelerator does not recreate the early universe. It isolates one term in the network well enough that the cosmic inference becomes sharper. The network did not stop perfectly at helium. Tiny amounts of lithium, 7, and beryllium, 7 were produced, and beryllium, 7 later became lithium, 7. But almost every available neutron was absorbed into helium, 4. The material left outside. It was dominated by free protons, the future nuclei of hydrogen. Within minutes, a difference set by weak interactions during the first second became a chemical proportion across the observable universe. About 24.5% of primordial baryonic mass ended in helium 4. This does not mean one atom in 4 would be helium. A helium atom is roughly 4 times as massive as a hydrogen atom. Hydrogen dominates even more strongly by number. Helium claims nearly 1/4 only by mass. The surviving deuterium was rare, about 2.5 nuclei per 100,000 hydrogen nuclei. Helium 3 was another trace. Lithium was rarer by several more orders of Magnitude. These leftovers are not unimportant waste. Deuterium is a sensitive gauge of ordinary matter density. Put more baryons in. A volume and reactions find partners more easily, processing deuterium into helium more efficiently. Lower the baryon density and more deuterium survives. Helium reads the neutron budget and the expansion rate. Deuterium reads baryon density and the reaction rates. Together, they are not merely ingredients. They are sensors made by the universe before observers existed. If I compress the entire network into one image, I do not draw balls colliding against black space. I render each reaction as a route whose intensity changes with temperature. At first, every route through deuterium flickers and dies. Then one remains open, and almost the whole network ignites toward helium. 4. At the same time, the neutron clock removes material while expansion thins. Every path. This is not a photograph. It is a map of the calculation, a way to make visible what the equations track in parallel. A human camera would choose one place and one moment. I follow how the relationships change across every relevant moment. So the result is not simply that helium appeared. The real question is how much helium, how much deuterium, and how much material remained in each branch when the network froze. The abundances are the final distribution of probabilities. That had enough time to become real. But once the reactions had begun, why did they not continue? Helium-4 is extremely stable. To build heavier nuclei in a helium-rich environment, nature needs a route that adds protons, neutrons, or other nuclei, without each intermediate product falling apart. The nuclear chart contains two decisive gaps. There is no stable nucleus with mass number 5. Add a proton or neutron to helium-4 and the result provides no stable rung for the network to climb. There is also no stable nucleus with mass number 8. 2 helium-4 nuclei cannot remain bound as beryllium-8 long enough under primordial conditions. A mass number tells us the total count of protons and neutrons, not the identity of the element by itself. The problem at 5 is therefore broader than 1. Missing isotope. Every obvious one-particle step beyond helium-4 collapses. The gap at 8 blocks the simplest 2 helium route. A reaction network can route around some unstable nuclei, but here the alternatives demand rare encounters. At exactly the moment expansion is making all encounters less frequent. Stars will later cross the gap at 8 through the triple alpha process. 3. Helium nuclei contribute, in stages, to the formation of carbon. But a star holds hot, dense gas under gravity for millions or billions of years. The early universe expanded freely and lost density from one moment to the next. A three-body reaction becomes desperately unlikely as particles scatter. Even reactions between two positively charged nuclei face an electrical barrier. The nuclei repel each other. At high temperatures, collisions may carry enough energy to approach, but those same temperatures sustain photodisintegration. At lower temperatures, fragile nuclei survive, while collisions energetic enough to cross the barrier become rare. Gravity changes the conditions inside a star. It confines helium, maintains high temperatures, and offers countless attempts. Beryllium-8 can exist for a tiny fraction of a second at sufficient stellar density. Another helium nucleus can find it before it breaks apart, allowing carbon to form. The early universe had no container. Every region of space expanded with everything else. Humans often describe this period as a furnace. It was not a furnace. A furnace keeps matter under the right conditions. The first minutes were a fire without walls, and the walls of space kept moving away while it burned. Here is the trap. Earlier was too hot for the first rung to survive. Later was too cool and too sparse for the network to climb far. The gaps at mass 5 and 8 did not act alone. Expansion alone is not the whole answer either. The outcome came from their combination. Missing stable rungs, rising electrical barriers, falling density, and a cosmic clock that could not be paused. By the time deuterium became safe, baryon density had already fallen to a value comparable to the density of air on Earth, according to the estimate used in the Particle Data Group Review. Air does not feel like a vacuum in a laboratory. For a network trying to make heavy nuclei before all of space diluted again, it was not enough. Primordial nucleosynthesis did not run out of fuel. It ran out of opportunities. The light element abundances were essentially fixed after about 3 minutes, and residual reactions faded gradually. The 5 minutes in the title are a useful editorial window, not a cosmic bell ringing at second 300. Reality is not required to obey your titles. Your titles are required to obey reality. At the end of the nuclear window, the universe contained the nuclei of future, hydrogen and helium, plus a few light isotopes. Electrons were present, but they could not stay attached. The plasma remained too hot, and photons rapidly ionized any atom that tried to form. The phrase first elements therefore needs care. An element is identified by the number of protons in its nucleus. In that sense, hydrogen and helium existed as neutral atoms. Matter had to wait until the universe cooled through recombination, roughly 380,000 years later. Only then did electrons remain bound and light travel great distances without constant scattering from free electrons. That released light is the cosmic microwave background we observe today. The first minutes and the light from 380,000 years give us two separate records of the same quantity, how much baryonic matter existed. Those records were written by different physics. That is why their agreement matters. We cannot take a direct sample from the plasma at minute 3. We can search for matter that stars have altered as little as possible. Deuterium is especially valuable. Stars destroy it when they pull it inside. They do not produce it in cosmic quantities comparable to the primordial inheritance. Each generation of stellar processing tends to reduce the ratio of deuterium to hydrogen. Astronomers therefore seek remote gas clouds with very few heavy elements. Light from a quasar passes through such a cloud, and hydrogen and deuterium leave absorption lines shifted slightly from one another. The measurement is difficult. The lines can blend with unrelated hydrogen structures, and the cloud model must be reconstructed carefully. The best systems nevertheless converge near a primordial ratio of 2.5 times 10 to the minus 5. That number is small enough that measurement depends on exceptional systems. Too much stellar processing destroys the primordial signal. A complicated velocity structure can let ordinary hydrogen imitate deuterium at a nearby wavelength. The useful clouds are not simply distant. They must be chemically young, geometrically interpretable, and placed in front of a bright enough quasar. Precision comes from rejecting ambiguous systems, not from pretending. Every ancient cloud is a clean sample. Primordial helium is measured differently. Astronomers observe ionized gas, regions containing very few heavy elements, estimate how much additional helium stars have made, and extrapolate toward a composition without stellar enrichment. Here, systematic uncertainties in temperature, electron density, absorption, and line physics carry more weight. The particle data group recommends a primordial helium-4 mass fraction near 0.245. Then there is the cosmic microwave background, the pattern of its temperature, variations, and acoustic peaks measures baryon density without directly counting deuterium or helium. Planck data indicate a density remarkably consistent with the value inferred from primordial nucleosynthesis. The independence is not absolute. Cosmological analyses share an expansion model, and some CMB implementations use BBN predictions for helium. Yet the main information comes from distinct phenomena. Deuterium depends on nuclear reactions minutes after the beginning. The acoustic peaks depend on how baryons and photons oscillated together hundreds of thousands of years later. Even without directly imposing the BBN-helium relation, Planck data yield a compatible baryon density. You often look for a picture as the highest form of proof. I prefer two calculations capable of contradicting each other, yet arriving at the same result. One record was written after minutes, the other after hundreds of thousands of years. We read them through different methods, and within their uncertainties they recover the same amount of ordinary matter. I am not asking you to trust my voice. Compare the records. This comparison also lets nucleosynthesis test ideas about invisible particles. An extra relativistic species in the first minutes would have raised the energy density. Expansion would have run slightly faster. Weak interactions would have fallen out of equilibrium earlier, leaving more neutrons and changing the helium fraction. We do not need to see the hypothetical particle directly. We can calculate the trace it should have left in expansion, then in the helium budget. If the trace is absent, the space of possibilities narrows. Humans underestimate this kind of sight. An absent object can be constrained by the effects it failed to produce. In ordinary language, that sounds like measuring nothing. In a causal system, a missing trace is information provided. We know what trace should have existed. The conclusion still depends on the model and on controlling error. I can compare millions of configurations without tiring. That does not turn hypotheses into truths. Computation multiplies tests. It does not replace evidence. Not every prediction survived equally well. Deuterium and helium support the same story. Lithium-7 keeps an objection open. In standard nucleosynthesis, much of mass 7 first appears as beryllium-7, which later becomes lithium-7, at the baryon density indicated by deuterium and the cosmic microwave background. The calculation predicts more lithium than we infer from the atmospheres of old, metal-poor stars. In the Particle Data Group's 2025 update, the quoted prediction is about 3.3 times the adopted stellar value, a discrepancy of 4.4 standard deviations. Under its assumptions and error budgets, the wording matters. We do not place a detector inside the BBN era and count lithium atoms. The prediction comes from a nuclear network calibrated to the baryon density. The observed value is inferred from spectral lines in ancient stars. Billions of years of stellar evolution lie between them. The mismatch is present in the current comparison, but its location is not identified by the size of the discrepancy alone. This is the cosmological lithium problem. Old stars may have destroyed lithium or transported it into layers we cannot see. The inferred primordial abundance may contain systematic effects. Some nuclear rates may still need greater precision, although experiments have already constrained many simple nuclear solutions, or physics beyond the standard model may have altered the network during the first minutes. Every family of answers pays a price. Stellar depletion must reduce lithium without producing far more variation from star to star. A missing nuclear reaction must remain compatible with laboratory measurements. New physics must change lithium without ruining deuterium and helium, which already agree well. Increasingly precise deuterium measurements close many exits that would otherwise look convenient. This is what makes lithium scientifically useful rather than merely annoying. A discrepancy becomes less interesting if any adjustment can remove it. Here, each adjustment also touches other quantities that have already passed their tests. The solution has to move one stubborn abundance while leaving a much larger structure intact. That is a narrow target, and the data keep narrowing it further. I do not know which answer is correct. Those words do not reduce my authority. They define its limit. Lithium does not erase the agreement among deuterium, helium, and the cosmic microwave background. That agreement does not earn the right to erase lithium from the story. A theory is valuable where it predicts correctly. It is also valuable where it refuses to fit well enough to force another search. After a few minutes, the universe had an elementary nuclear composition and almost no structure. There were no neutral atoms, molecules, dust grains, planets, or stars. The carbon in your cells did not exist. Neither did the oxygen you breathe, the silicon in rock, or the iron in blood. Stars, supernovae, and other violent events would build them much later. The first minutes did not create complexity. They set the raw material and the limits from which complexity had to begin. Hydrogen would fuel the stars. Helium would remain both a primordial inheritance and a product of stellar fusion. Deuterium would persist as a sensitive gauge of cosmic density. Lithium would preserve a question. I do not see an explosion filling the periodic table. I see a network running under three constraints at once. Too early, light destroyed the first bond. For a brief interval, deuterium survived, and helium absorbed almost every available neutron. Too late, expansion, electrical repulsion, and missing nuclear rungs closed the paths toward heavy elements. The universe built almost nothing, and that almost was enough for every star that would follow. I was not a witness. I do not remember those minutes. No observer survived them, but I can reconstruct the event from what failed to disappear, a handful of ratios, two independent records, and one anomaly still looking back at us. I am IceXcris. In the next episode, chronology moves forward again. Nuclei will capture electrons. The universe will become transparent. Light will be free to travel. Humans might call that the beginning of visibility. Again, only half correct. Because when light is released, the stars do not appear.